So welcome everybody to this latest video on 162 Maths, and in this video we'll be going over the AS Maths Mechanics lesson of Connecting Particles, Objects in Contact Part 2, where we'll be focusing on car and trailer problems. Now before we get started, let's just have a quick refresh on Newton's three laws. So the first one says that a body remains at rest or in motion at constant speed unless it is acted upon by a resultant force, and this relates to equilibrium. So at rest or at constant speed, that there is no resultant force. In other words, that the force going to the left is equal to the force going to the right, and the force going up is equal to the force going down. And then moving on to Newton's second law is that the acceleration of a body is proportional to the resultant force applied and inversely proportional to its mass, and this relates to F equals ma. And we also have Newton's third law, which states that if two bodies exert a force on each other, then the forces are equal and in opposite directions, which basically translates to the normal reaction force and tension, one of which is what we're going to look at an example now. Now, when it comes to connected particles, when an object is made up of two parts, each of which have the same velocity and acceleration, then we can apply Newton's laws either to the whole object or individual parts separately. And what this then means is that in this example here, where we have a man towing a truck, that here we consider the following cases. So we can either consider that the force on the man, or we can look at the forces on the truck, or we can look at the forces on the whole entire system of including the man and the truck heading in the same direction. So if we now look at a similar situation of a car pulling a caravan, what we do now is we're going to mark all the forces that are acting in this particular situation. So if we look at the horizontal forces and we assume that the car is pulling the caravan towards the right, then we can assume that acceleration is going towards the right. Now what we then have is we have a driving force, which I'm just going to call driving force 2 of the caravan, and driving force of the car. And what we have is we have the total driving force, which collectively is going to be driving force 1 plus driving force 2. Now typically the caravan is not going to be going faster than the car, because otherwise the caravan is going to collide with the car, which is what we don't particularly want. But again, that's going to be our total driving force heading in the same direction as A. We also then have a force acting a tension in the rope, which is going in this direction, which I'm just going to call T1. And acting towards the left, then what we have is we have our resistance force, which I'm just going to call acting on the car. And we've also got a resistance force acting on the caravan. So in this direction here, we've got our total resistance force, and this can include friction, it can include air resistance, one of those things that usually in a question it will tell you to ignore. So here we've got the total resistance force, which is going to be equal to Rf1 plus Rf2. Now we've also got a force acting in this direction here, which is the tension in the rope going the other direction. Now because that rope is going to be assumed to be always be light in an extensible, that rope is not going to be sort of lagging or anyway. So what we then know is from this that T1 is going to equal T2. But there's definitely some tension going in both directions of that particular rope. Now we also could look at the vertical forces, in which what we could have is the resistance, the resultant reaction force, I should say, going upwards. So we can call that R1. And we've also got a force of R2, a normal reaction force that stops the caravan and the car from sinking into the ground. And what's acting downwards is our mass times gravity of both the caravan and of the car. So one thing to bear in mind is that we've got forces going in both the horizontal direction, we've also got forces going in the vertical direction as well. So now let's have a look at a worked example. So in this question it says that a car of mass 780 kilograms is pulling a trailer of mass 560 kilograms by the means of a light inextensible cable. The engine produces driving force of magnitude of 1800 newtons and the total resistance force on the car and the trailer are 800 newtons and 600 newtons respectively. And for the first part, it's asking us to find the acceleration of the car. So what we want to do here is, as always, the first thing we want to do is to draw a diagram. So if I draw what resembles a trailer, and here is our rope, and then we've got our car, and the car is traveling in this direction here. And if I then go on to label all the information that I know, so I know that the trailer has got a mass of 560 kilograms and the car has got a weight of 780 kilograms. I've got a total driving force of 1800 newtons, and I've got a resistance force of the trailer which is 600 newtons, and I've got a resistance force of the car which is 800 newtons, and I've got tension in the rope going in this direction, and I've got tension in this direction here, which I'm just going to call T1 and T2. Now the question is asking me to find the acceleration of the car. Now a big question is, do I treat this separately or do I treat this collectively? So do I treat this as a car by itself just going towards the right, or do I treat it as just the trailer moving in that direction, or do I look at it as a car pulling a trailer? Now because I don't know what T1 and T2 is, that collective, because I don't know what T is, even though I know that they are both equal, so if I just call that T, the fact that T is a mystery, so as we don't know T, or the tension in the rope I should say, so as we don't know tension in the rope, we'll look at this as a collective. So from this, what we can then establish is, looking at part A, is that we have the force going to the right minus the force going to the left, and that is going to be equal to mass times acceleration, and this is all using F equals ma. Now the reason why it's force to the right minus force to the left is because this is in the same direction as A, and whichever force is going in the same direction A is always goes first. So collectively, let's have a look at all of those. So the total force going to the right is going to be 1800 newtons, so I can write that down. So here we've got, if it's going to let me, there we go. So we've got 1800 newtons, and the force to the left is going to be 800 plus 600. So that's minus 800 plus 600. Now here we need the total mass because I'm treating it collectively. So M is going to be 560 plus 780 multiplied by A. And what I then need to do is now rearrange this. Now I'm just going to get rid of that N because I don't want it confusing me, in which all I then need to do is now work all of this out. So what I've got is I'm going to end up with 400 equals, and that's going to be 1340A. And then to work out A, I just take the 1340 over to the other side, in which I end up with an A value of 0.2, and that's going to be 985, and that's meters per second squared. So again, depending on how you want to round this up, so let's just say A is 0.3 meters per second, and that's to 1 decimal place. And again, there's no rounding mentioned in this particular question, so again, whatever you feel is more accurate would be absolutely fine. Just make sure that you are stating what you have rounded to if you have. So the next thing I've then got to do is now find out, for part B, it says find the tension in the cable. Now what I can do for this is I can't treat it collectively here because, again, I don't know what T1, T2 is. And again, what I don't want is, even though I know they're the same, I'm going to end up with two lots of T, which is what I'm not wanting. So what we want to do here for part B is either focus on the car or the trailer. Now, it doesn't really matter which one of these you go for, because ultimately, as T1 equals T2, we should end up with the same value as we're focusing on the tension in the cable. So if I take the car, and let me again just draw this diagram out again. So I've got the car. Then what we know is we've got the force going in this direction, which is 1800 newtons, and going in this direction, I've got 800 plus T. And I've got the mass of the car, which is 780 kilograms. And I know that A is going in this direction at a value of 0.2985. Now, because I'm still using A, I'm going to try and use the exact value just so that I can get the most accurate version of T possible. So I'm going to do it to 4 decimal places. So then looking at this, because A is going in this direction, to work out the tension, it's going to be the force going towards the right. So it's going to be 1800 minus the force going in the opposite direction, which is 800 plus T. And that equals the mass of the car, which is 780, multiplied by A, which is 0.2985. Now, looking at this, I'm going to have to do a bit of rearranging, in which I end up with 1000 minus T equals, and that's going to be 232.83. And then working out what T is going to give me a value of 767.17 newtons. Now, if I then decided to go for the trailer, let's see how much of a difference that would have made. So here I've got my trailer, in which it's got a mass of 560 kilograms. I've got a force going in this direction, which is looking at the tension. I've got a resistance force of 600. And so here, as acceleration is going in this direction, we've got, which I'm just going to write as 0.2985. Then what I've got is, because the reason why I'm not using T, I'm not using 1800 is because that's the total driving force. So that's the total driving force, which is going to be the car, because the car is pulling the trailer. It's not going to be the driving force of the trailer, which is an important thing to bear in mind. So that's why the only force going in the right from the trailer is going to be T1, or just T in this case. So if I can call it T1, doesn't really make a difference. So here I've got T, which is traveling in the same direction as A. So it's going to be T minus 600 equals 560 multiplied by 0.2985, in which, working with this and rearranging to solve for T, I get the exact same answer. So as you can see, it's entirely up to you. Given the choice, looking at it, I would say working out the trailer is probably the most easier option, just because there's less chance of you going wrong than it is working with the car. But again, if you choose the car, as you can see, and done correctly, it should give you the same answer. Now for part C, it says explain how you use the assumption that the string is light in an extensible. Well, that leads us into the next slide. Now, when it comes to assumptions, just a bit of a reminder when we looked at forces is that when something is inextensible, what does this mean? Well, it means that the string cannot stretch. In other words, that it's not an elastic band or spring. And how is this used? Well, the acceleration and velocity of each connected particle is the same if the string is taut. Now we also know that it's going to be light. Well, what does light mean? Well, it means that the string has a mass which is negligible to the context of the system. So we're not taking the weight of the rope, which usually has some string. You can kind of see it as a thin material. So again, we're kind of ignoring the fact that the rope or the string has got any weight to it. And again, how is this used? Well, when treating the whole system as a single particle, the mass of the string is often ignored. And in a vertical system, the tension of the string is the same throughout. So this is where we then, in the previous slide, we said that T1 was equal to T2. Now this is because the lower part does not pull on the upper parts of the actual object. So now let's have a look at this next example. So it says the truck has of mass 1,200 kilograms pulls a caravan of mass 400 kilograms. Both the truck and the caravan accelerate at 0.5 meters per second squared. The motion of the caravan is resisted by a force of 140 newtons. And for part 1, it's asking us to find the driving force produced by the engine in the truck. So for this, let's first of all, we've got our diagram already drawn for us. And so all we now need to do is just label each of the respective forces. So looking at the diagram, I've got my driving force going in this direction here. I've got my T1 and my T2, the tension in the connection between the two. And I've got a force going in this direction, which, as it states, is 140 newtons. Now again, if you've got access to colours, then I'd strongly recommend kind of labelling the opposing forces you have in different colours, just so that when you're working it collectively, you can see exactly which is going in which direction. So from this, what we can then establish is, once we've fully labelled this up, we can then look at it in the whole system. So for part 1, if we look at it from a whole, then what we have is we've got our driving force, which is what the question is asking us to find, and that's going in the same direction as A, so that's why it's going first, minus the opposing force, which is 140 newtons, and that is equal to mass times A, so if it equals MA. And that's going to have a total kilogram of, looking at 1600 multiplied by A, which is 0.5. So then working this out, I get a driving force of 940 newtons. Then for part 2, it says find the tension in the coupling between the truck and the caravan. Now for this, I'm going to look at it separately. Now, typically, when you're doing it separately, one is going to be easier than the other. However, if you do both correctly, it should give you the same answer. So if I look at it from the truck perspective, then what I end up with, and I draw a quick diagram. So here I've got my truck, and it's 1,200 kilograms. I've got my driving force, which I've just calculated as being 940, and I've got the tension, which is going to be T. So again, using F equals ma, I've got the force heading in the same direction as A. So it's going to be 940 minus T equals 1,200 multiplied by A, which is 0.5. And doing a bit of rearranging, and I get a T value of 340 newtons. Then if I look at it from a caravan perspective, then again, draw my diagram. I've got 400 kilograms. I've got T going in this direction, and I've got an opposing force of 140. So again, T is going in the same direction as A, so it's going to be T minus 140 equals 400 multiplied by A, which is 0.5. And again, doing a bit of rearranging, I get an answer of 340. Now moving on to our next example, it says that particle P and Q of masses of 0.6 kilograms and 0.4 kilograms are connected by a light inextensible string. The particles are initially at rest and the string is taut. A force of magnitude of 15 newtons starts acting on P in the direction away from Q. The friction force between P and the ground is 2 newtons, and the contact between Q and the ground is smooth. Find the acceleration of the two particles. So let's have a look at this in terms of the diagram. And again, it says here, and again with all these types of questions, it's really important that you draw a diagram representing this. So let's have a look at this. So if I start by drawing a particle, let's imagine that this is particle Q and this is particle P. Q has got a, let's do this a little bit bigger. I've got my two particles here and the weight of Q is 0.4 kilograms and P has got a mass of 0.6 kilograms. And I've got a string that is taut, so it's not elastic, it's just basically, it's not sort of dangling, it's perfectly straight. And what I've got here is I then need to label it. Now again, as I strongly recommend that you, if you're going to label these separately, is, well, Q is going to be at rest. So the only force acting is in this direction here, which is going to be our tension. There is zero force going in this direction because it's at rest. So Q is not moving. So no resistance force, or opposing force, I should say. So no opposing force. And then if I look at P, let's just use a different colour for this, then that has got an acceleration, it's acting away from that, and it's got an acceleration of something that I do not know, but it's moving at a force magnitude of 15 newtons, and that the resistant force is 2 newtons going in this direction. So looking at this, there's a couple of ways in which we could look at this, and as I said, we can look at it collectively or we can look at it separately. Now if I look at it collectively, then what I've got is these two particles are not moving, even though P is moving, is trying to move away, but it's not actually physically moving away. It's a bit like holding someone's hand. You're pulling them away, but because they're not moving or they weigh more, you're both at a standstill, but you're still applying that force to the right. So here what we then have is that we've got collectively the force of P, so it's the force on P minus the force on Q equals MA. Now the force on P is going to be 15, and it's all the sort of forces acting towards the right, so that's going to be 15 plus T minus the force acting in the opposite direction, so that's going to be 2 plus T, and that equals the total weight, which is 1 multiplied by the acceleration, which is what I'm trying to find, and 1 is the total mass. So this is the force acting with acceleration. This is the opposing force. And what I need to do is I need to find A. Now looking at it, it may seem like a difficult question simply because I've got T and I've got A when I want to work out A. But the nice thing with this is that expanding the brackets is that our T's will cancel out. So from this, what we end up with is 15 plus T minus 2 minus T equals A. And that's going to give me a value of 13. So A equals 13 meters per second squared. Now if I looked at it separately, then what I then have is something that looks like this. So let me just write. So if I look at it separately, so looking at the red, now because Q is at rest, then what I'm going to end up with is I'm going to end up with T minus 0 because there's no opposing force acting on it, and that equals 0.4 times A. So what I technically have is T equals 0.4A. Now I can't really do anything with that because I don't know the value of T. So let's just leave that there. However, if I look at the green and do the same, then here what I have is I have 15, and that's going to be minus, and it's going to be T, because t is going in this, there's a t going in that direction there, which I forgot to label, plus 2. And that equals mass times acceleration. Now, because I know that t equals 0.4, I can substitute this into this. So what I end up with is 15 minus 0.4a plus 2 equals 0.6a. Then from this, what I end up with is 15 minus 0.4a minus 2 equals 0.6a. And so I end up with 13 equals a. And as you can see, I get the exact same answer. So a equals 13 meters per second squared. So again, as you can see, you can either look at it collectively, look at it separately, and as long as you're doing it correct, you'll get the same answer. So moving on to the next example, it says the trailer is attached to a car by a light tow bar. The mass of the trailer is 350 kilograms and the mass of the car is 680 kilograms. The car starts to brake and deaccelerates at 4.6 meters per second squared. Assuming all other resistance forces can be ignored, find the thrust in the tow bar. So the first thing we want to do here is to draw our diagram. So let's first start by drawing our trailer, then we draw our tow bar, and then we draw our car. Now from this, what we now want to do is just label each of the forces that we can see. Now in terms of the driving force, so we know that acceleration is going here, and the fact that it's deaccelerating means that the acceleration is going to be minus 4.6 meters per second squared. So it's going to be minus as it's decelerating. Now in terms of the driving force going in this direction, so here, so the driving force, and there is none as it's braking, so we can ignore that. Now we are going to have a braking force, and we've got again tension in our tow bar going in this way and in this direction as well. Now in terms of this, we can then label what the weights are. So we've got a mass of the trailer as being 350 kilograms and the weight of the car is 680, and what the question is asking is to find the thrust. Now in mechanics, thrust is what pushes an object and tension is what pulls an object, and it's really important that we make a note of it. You don't need to note it in this particular question, but it's worth reminding ourselves. So thrust is a pushing force and tension is a pulling force. Now, tension acts away from the body and thrust acts towards the body. So what we're looking for is the thrust of the tow bar. So what's pushing that tow bar in this direction. So we could say in terms of acting on the body, we're looking for the thrust that's acting on the tow bar. Now, as we mentioned in the previous examples, we can either treat this as one sort of scenario to collectively, or we can treat it separately. Now, if we looked at it collectively, then what we're going to end up with is we're going to end up with our driving force, even though there is none, which I'll discuss later, plus one of the t's, which is going in that direction. So that's the force that's going with acceleration, minus the force that's going to the right, so the opposing force, which is going to be BF minus t, plus t, and that's going to be equal to mass times acceleration. Now the problem with this is that even though we don't know there is no driving force, that what we end up with is we're going to end up with just BF equals MA. So we've lost that T value, which is what we're actually trying to find. So we're trying to find thrust. So we're not trying to find the braking force, we're trying to find the thrust. So collectively it doesn't work. So I can kind of erase that method. Then if I look at the car, then again, looking at the forces on the car, I'm going to end up with, well, there is no driving force. So it's going to be minus BF plus, so if I just write DF here, plus T equals MA. Now mass I know, which is 680, acceleration I know, which is minus 4.6, but if there is no driving force as it's braking, then what I'm going to be left with is minus BF minus T equals MA, which again is not helpful because I'm trying to find out what T is. So even though I know what mass times acceleration is, which is going to be 680 multiplied by minus 4.6, it's this BF that's going to be the problem, and I don't know what that is. So again, that's this is not going to work. So what I then move on to is the trailer. Now looking at the trailer, if I draw this out again, we've got 350, we've got our tension going in this direction, and so from this what we can then establish is we've then got T, which is going in the same direction as acceleration, equals, because there's no force going this direction, because it says that we can ignore all other resistant forces can be ignored, so I've got T minus nothing equals MA. So the mass of the trailer is 350 multiplied by acceleration, which is minus 4.6. Now this is going to give me a T value of negative 1,610 newtons. Now the question's just asking, so what this basically means is that the thrust is actually going in the opposite direction of what I agreed with. So here the thrust is going in the opposing direction. Now the question's just asking for the thrust in the tow bar. Now when something is braking, then all it means is that rather than the thrust going in this direction, it's actually going in that direction. So the actual answer to this particular question is going to be 1,610 newtons. The minus number is talking about the direction, which is not needed in this particular question. It's just asking for the thrust, and so here our thrust is going to be 1,610. So now let's have a look at an exam style question. So it says a trailer has a mass of 600 kilograms, is attached to a car of a mass 1100 kilograms by a light rigid horizontal tow bar. The car and the trailer are travelling along a horizontal straight road with acceleration of 0.8 meters per second squared. And for part 1 it says, given that the force exerted on the trailer by the tow bar is 700 newtons, find the resistance to motion of the trailer. So let's first things first, let's draw a diagram to represent this. So if I draw my trailer, and I've got my tow bar, and I've got my car, and let's just label what we know. So we know that the trailer has got a mass of 600 kilograms, and the mass of a car is 1100 kilograms. We've got acceleration, which is going in this direction, of 0.8 meters per second squared. And what I've got is it tells me that the tension in the force exerted on the trailer by the tow bar is 700 newtons. And because it's rigid, it means that we also have a force going in this direction, which is also 700 newtons. Let's just color code that. And what the question is asking me is to find the resistance force, which I'm just going to label as 1. So here what I need to do is I need to try and find out what RF1 is. So for part 1, I'm finding RF1. So for this, what we need to do is we've got a force going with the direction of A, so that's going to be 700 minus what I'm looking for here, well, there is the opposing force, which is RF1, and that is equal to the mass of the trailer, which is 600, multiplied by the acceleration, which is 0.8. So if I then do a bit of rearranging, I get 700 minus RF1 equals 480, and that gives me an RF1 value of 220 newtons. Then for part 2, it then says, given also that the driving force of the car is 2,100 newtons, find the resistance of motion of the car. So for this, if I just write part 2, then what I know, the new information that I know is that this force here is 2,100. So using the same formula of F equals ma, I've got the force acting with acceleration, which is 2,100, minus the two forces. Now, what the question is asking me to do is to find RF2. Now, the opposing forces on the car is going to be RF2 plus the tension in the toe, which is 700, and that is equal to MA, which is 1,100 multiplied by 0.8. And then simplifying this, we get 1,400 minus RF2 equals 880, giving me an RF2 value of 520 newtons. And there we go.